Good afternoon. We take forward our discussion on the amorphous solid dispersions, and today we are going to talk about the role of polymers in the amorphous solid dispersions. In this, we are going to learn what type of polymers are used for designing the ASDs and what exactly is their role in the stabilization and solubilization that is achieved from the amorphous solid dispersions. This slide captures the type of polymers that have been utilized for the manufacturing of amorphous solid dispersions. We have polyvinyl class of polymers that includes PVP, PVA, PVPCl, PVPVA, and PVAP. And if you remember in the table that we had shown earlier in the previous class, PVP and PVPVA are part of the commercialized ASD products as well. The next category of polymers is cellulosic polymers, and HPMC is one of the most common polymer that has been used. And apart from that, we also discussed that HPMC AS has lately become a very popular polymer for the designing of the ASDs. You can also use eudragids. They have pH dependent solubility, and then polyethylene glycol and polyethylene oxide type of polymers have also been used for the designing of the ASDs. In terms of the commercialized products, the most common polymers are HPMC AS, HPMC, and PVP. When we design a amorphous solid dispersion, there are two components that are present in the ASD. One is the polymer and the other one is the drug molecules. The drug molecules are dispersed in the matrix of the polymer. So there are three possibilities that can occur in terms of the phase structure of the ASD. The first one is the most desirable state, wherein you have molecular dispersion of the drug in the matrix of the polymer. These black color strands indicate the polymer molecules, and these red colored dots are the molecules of the drug. In this particular scenario, you see that the molecular dispersion of the drug is present in the polymer matrix, which means the molecules of the drug are separated out from each other and they are not in contact with the neighboring drug molecules. The second type of phase structure that can be present in the amorphous solid dispersion is something like that, wherein a phase separation has occurred. The polymer rich zone has been formed, and then there are drug rich zones. Remember, in this particular situation, the crystallization of the drug has not started, only a phase separation has taken place. In a way, you can consider that if you store this particular sample at a temperature and humidity condition, with the time it will start converting into this type of scenario, wherein there is a phase separation of the polymer and the drug, and we achieve what we call as the polymer rich zones and the drug rich zones. The third stage is wherein the polymer rich zones have separated out and the drug molecules have now nucleated and crystallized out in the amorphous solid dispersion. This would be an undesirable scenario, because since the drug has now crystallized out, the solubility benefit that we were trying to achieve from the amorphous form would no longer be achievable. So in terms of the desirability, while the development of the ASD, we would ideally like our system to be like this, wherein the drug is molecularly dispersed. Subsequently, it may convert into a phase separated phase, and then subsequently the crystallization of the drug may take place. As I told you, this is something which we do not want to happen in our sample. Drug polymer miscibility is a very important aspect for the designing of the ASD, and we would like that our drug molecules are miscible in the polymer matrix that has been taken for the designing of the ASD. Now, this is the phase diagram. On the x-axis is the temperature, and on the y-axis is the amount of drug in the polymer. There are various zones that are shown here. So this dotted line shows the Tg of the polymer and Tg of the solid dispersion. So you can see that as the amount of the drug in the polymer is increasing, the Tg of the polymer or the Tg of the amorphous solid dispersion will start decreasing a little bit, because polymers typically will have high Tg value, while the amorphous drug has a lower Tg value. So a combination of the amorphous drug and the polymer will show a slight decrease in the Tg value. This line shows the crystalline drug polymer solubility line. Now we have to differentiate between two terms. One is called as the drug polymer miscibility, and the other one is called as the drug polymer solubility. We will use the term solubility when the drug from the crystalline form has been dispersed in the polymer. In that case, we are going to use the term drug polymer solubility. If the drug was in the amorphous form and the value of the drug that is dissolved in the polymer would now be called as drug polymer miscibility. So repeating the concept again, if the drug was initially crystalline, then the terminology would be used as drug polymer solubility. And if the initial drug was amorphous, the terminology we will use is drug polymer miscibility. So this is the solubility line, and this is the miscibility line. So this is crystalline drug polymer solubility line. This is amorphous drug polymer miscibility line. And as we discussed, this is the line of the glass transition temperature of either the pure polymer or the amorphous solid dispersion. This zone 1 is the thermodynamically stable zone, because we are in the area which is below the glass transition temperature. So 1 is below the glass transition temperature and 2 would be above the glass transition temperature. So herein, if you have your ASD in this zone, it is going to be a thermodynamically stable system, because the solubility or the amount of the drug in the ASD is below the solubility of the crystalline drug in the polymer. However, practically this zone is not very useful, because the value of the drug that is available in the ASD in this zone is going to be very, very low, which means the drug loading in the ASD is going to be very low. This zone 3 is the kinetically stable or supersaturated glass zone, because here you have the drug which is below the miscibility value. Miscibility, remember, comes from the amorphous drug. So this is going to be a kinetically stable, but it is going to be a thermodynamically unstable zone. Most of the amorphous solid dispersion that are there in the market are designed in this zone, wherein we operate in the region where the drug content is below the miscibility value, and it is in the kinetically stable zone. Zone 5 is the immiscible or the supersaturated zone. So if you operate in this particular zone, it is highly likely that the drug will separate out in the amorphous solid dispersion, and subsequently crystallization will take place. So we have only considered zone 1, 3 and 5, because these are the zones which are below the glass transition temperature of the polymer or the ASD. Remember, in the practical scenario, we are always interested in a temperature zone which is usually below the Tg of the system. because above the TG of the system, the system will enter into the supercooled liquid state where it is going to be highly unstable. So that is why we have not discussed about zone 2, 4 and 6, because those are the zones related to the supercooled liquid state, whereas zone 1, 3 and 5 are related to the glassy state. So remember, we would like to design our ASD in most probably the zone 3, because it allows us the optimal drug loading. At the same time, the system is kinetically stable and it can remain in the form of the amorphous solid dispersion throughout the shelf life. The mechanisms that are responsible for stabilization of the amorphous drug by the polymers are numerous. So the first mechanism is called as the anti-plasticization of the drug, which is nothing but increase in the TG value of the drug by the addition of the polymer. Since the polymer has a relatively high TG value, so on combining with the drug, the overall TG value is going to increase, and this is called as anti-plasticization. Reverse of it, when the TG decreases, is called as the plasticization. The second mechanism are the intermolecular interactions between the drug and the polymer, and among them the most prominent ones are the hydrogen bonding, ion dipole interactions, van der Waal interactions and London forces. These will also keep the amorphous drug into a relatively stabilized state. The third mechanism is the reduction in the chemical potential of the drug. Since the chemical potential of the amorphous drug is higher, that is why it is unstable. So in the amorphous solid dispersion, there is a reduction in the chemical potential so that the stabilization can be achieved. The last mechanism is the molecular mobility reduction because of the presence of the polymer, and the reduction in the molecular mobility takes place because there is a physical barrier to crystallization because of the presence of the chains of the polymer in the ASD, because of antiplasticization and because of intermolecular interaction. So all these four mechanisms will overlap in a zone which is called as the sweet spot. So to attain the optimal stabilization in an amorphous solid dispersion, we should have a system wherein the drug and polymer allow us to achieve this sweet spot, which means an overlap of all these mechanisms, giving us the most optimal stability of the amorphous solid dispersion. Coming over to the selection of the polymers for the ASDs, what are the criteria that have to be used for choosing a polymer for a particular amorphous solid dispersion? These are the approaches that are used for choosing the polymers. So the first approach or method is an empirical method wherein you choose common polymers and melting point and solubility is considered as one of the additional aspects here. The other approach is the approach related to the manufacturing procedure that you are going to use. As we told, spray drying and the hot melt extrusion are the two most common methods that are used for the manufacturing of ASDs. So based on what method you are going to use for manufacturing, you will choose the optimal polymer. So if you are going to use the hot melt extrusion method, there is a need to choose low melting polymers, because if the melting point or the softening point of the polymer is high, there are chances of degradation of either the drug or the polymer. In contrast, if you are going to use a spray drying process, then the solubility in the solvent that is going to be used for spray drying is going to be a very important criteria, because both the drug as well as the polymer have to be dissolved in a common solvent system before you spray dry them. Another important parameter that helps in the choice of the polymer are the solubility parameter, which can be calculated theoretically based on the chemical structure of the polymer. So if the polymer solubility and parameter are similar with that of the API, it is considered to be a good choice for that particular drug, because it then allows maximum mixing and promotes miscibility. Next criteria is that of miscibility. The polymer needs to be miscible for the API for generation of a successful ASD. Some of the polymer properties that are important for their selection into ASD are it should have a high glass transition temperature, and polymers that have a low water sorption are preferred, because if the water vapor sorption is more in the polymer, the water is going to reduce the glass transition temperature, as it is a very strong plasticizer. So we normally would like to pick up a polymer that has low water sorption capacity. Another approach is doing the DSC of the drug and the polymer, and we can determine the TG by TM ratio of the drug. So high ratios may resist the crystallization, and if you have a low ratio of TG by TM for the drug, which means it will have a greater tendency of crystallization, and based on that you will have to maybe use a higher quantity of the polymer for stabilization. Similarly, some other parameters that can be calculated are reduced crystallization temperature. Crystallization peak in the DSC increases in temperature with increased interaction between the API and the polymer. In the DSC, what is done is that you run a heat-cool heat cycle, and in the third heating cycle, you will observe a recrystallization peak of the drug. And based on that, this reduced crystallization temperature can be calculated. Next aspect is determining the width of the TG of the drug. So if the drug has a wide TG over a temperature range, then it may indicate partial miscibility of the drug with the polymer. Then you can look at the possible chemical interactions between the amorphous drug and the polymer, and we can look at common hydrogen bonding motifs, ion dipole interaction, or acid base interactions between the drug and the polymer, because this will then maximize the interactions between the amorphous drug and the polymer, which is one of primary mechanisms for the stabilization of the amorphous solid dispersions. Another important criteria is that the amorphous solid dispersions are falling under the category of supersaturated drug delivery systems, because they release the drug in a solubility value which is higher than the saturation solubility of the drug. Whenever you go into the supersaturated state, there is a possibility of the recrystallization of the drug. Some of the polymers have the capacity to prevent this recrystallization and maintain the supersaturation for a longer period of time. So we need to determine the polymers that improve supersaturation or stability in the solution form. So those polymers are going to be preferred for the designing of the amorphous solid dispersion, because they can maintain the supersaturated state for a longer period of time. So if we want to summarize the selection criteria for the polymers for designing of ASDs, they are listed out here. We want a polymer that has a relatively high TG, because it will then exert an anti-plasticization effect. The polymer should have complementary functional groups as that of the drug, so that hydrogen bond donors and acceptors can interact between each other. If your drug has hydrogen bond donors, then you can pick up a polymer that has hydrogen bond acceptors. That will maximize the possibility of hydrogen bonding between the drug and the polymer. Miscibility of the polymer with the drug is also very, very important, and you can see this by running a DSC. If you get a single TG value for your amorphous solid dispersion in the DSC, it means that the drug and the polymer are miscible. But if you see two different TG values, this means that the drug and the polymer are not miscible with each other, and they are lying independent of each other in the amorphous solid dispersion. Molecular level mixing of the drug and polymer combination is important aspect, and polymer creates hindrance to the crystallization of the drug by reducing the molecular mobility, by acting as a physical barrier between the different drug molecules that are present in your amorphous solid dispersion. Now we are going to stop here, and in the next class we are going to discuss a very important aspect with respect to the decision trees that are followed in the industry for selection of the amorphous solid dispersions, which means we are now going to look at the practical aspects of how the amorphous solid dispersions are designed in industrial R&D lab. So if you have any questions, you can post it on the WhatsApp group. Thank you very much.